things, temps and screen is yours. You can
Okay, thank you.
deliver this course this morning.
Okay, I will start. Let me share my screen here and go to slideshow mode. Okay, so my last presentation, obviously the fifth presentation in this series among the US lecturers, is going to be about groundwater geochemistry and groundwater contamination. And I'm going to focus more on the geochemistry than on the contamination. But what I want to do is just start out kind of doing a quick review of aqueous chemistry. And I realize that some of you may be familiar with this already. For others, maybe you have had this information previously, but it has been a while. So, of course, mass can occur beneath Earth's surface or on or above the surface as a solid or as an amorphous phase. So sometimes we call amorphous phases solids, but strictly speaking, the definition of a solid is something that has long-range molecular order. So for example, a crystal is a solid, but glass is not, because glass doesn't have the long-range molecular order. Of course, mass can occur as a gas, as a liquid, or as a solute. And so we've already talked about, in terms of porosity, for example, the solid phase and the liquid phase, and in the vadose zone, the gas phase. But we're going to spend a lot of this class talking about solutes, which is basically dissolved mass, either dissolved solids or dissolved gas, other dissolved liquids, or dissolved amorphous material. So most inorganic solutes are what we call electrolytes, which means that when they dissolve, they dissociate into ions. Cations are positively charged and anions are negatively charged. So the example I usually use is sodium chloride or halite, basically table salt. When it dissolves, it dissociates into the sodium cation and the chloride anion. But there are also compounds that when they dissolve do not dissociate. They are non-ionic. And so when they dissolve, instead of forming ions, they dissolve as molecules. Because water is polar, because it has regions of the molecule with a net positive charge and a net negative charge, even though overall it is neutral electrically, electrolytes tend to dissolve relatively easily in water because cations can align along the negative part of the water molecule and anions can align along the positive part. Whereas non-electrolytes tend to be relatively insoluble in water. So this next slide just shows the water molecule and how it is polar, that is, it's charge balanced, but the charge is asymmetrically distributed. So you see the dipole, as it is called, with the oxygen has the negative charge, and the hydrogen atoms tend to have positive charge. And so water molecules orient themselves around ions relative to the positive and negative parts of the water molecule. Whereas the lower diagram shows methane, CH4, which, like a lot of organic compounds, is nonpolar. That is, the charge is relatively evenly distributed. And consequently, these nonpolar compounds, because they do not tend to bond with water in the same way, that is, electrostatically, do not dissolve as readily in water. So I skipped the thermodynamics. I thought that I would just keep things relatively simple. But note that both solids and gases, and other liquids for that matter, dissolve until saturation is reached. And the solution is defined as being at chemical equilibrium with respect to the reactant, the solid, the gas, or another liquid, when the reactant is at saturation. There are other ways to define equilibrium. That is the rate of the forward reaction, say dissolution, is equal to the rate of the back reaction, say precipitation, or it can be defined thermodynamically in terms of the Gibbs free energy. But we'll just focus here on saying that when the solution is saturated, basically no more of that solute is able to dissolve. So when it is undersaturated, the compound that is dissolving has a tendency to dissolve. When it is supersaturated, the compound has a tendency to precipitate or exsolve. So you may be thinking, how can a compound, or rather, how can water become supersaturated with respect to a particular compound? And the answer is that saturation is a function of pressure and particularly of temperature in aqueous solutions as well. So the analogy that I draw with my students in class is if you think of dissolving sugar in a cup of coffee or a cup of tea, when that coffee or that tea is hot, the sugar dissolves relatively easily. But if you cool the coffee or the tea, then if you have dissolved sugar to the point of saturation, as the solution cools, the sugar will start to precipitate out because at a lower temperature, the amount that can be dissolved is less for most solids than at a higher temperature. The opposite is true for gases. The solubility of gases increases as temperature decreases. And conversely, gases become less soluble as temperature increases. That's why in order to get dissolved air out of water, you boil the water. And finally, note that dissolution and precipitation reactions tend to be reversible. So as I mentioned with the analogy of hot coffee or hot tea and sugar, that you can dissolve the sugar at a particular temperature, and then as you change the temperature, or as you make it lower, then the sugar precipitates back out in order to reestablish equilibrium. Not all reactions are reversible. Decay reactions like radioactive decay or oxidation reduction reactions are not immediately reversible. And I'll talk more about oxidation reduction reactions later. When we talk about solutes, it is customary in aqueous geochemistry to talk about the concentration of a solution with respect to different solutes like sodium or chloride or bicarbonate or sulfate. But you can also describe the overall salinity of the water as total dissolved solids. Now, total dissolved solids is a parameter that doesn't necessarily tell you what the dissolved solids are. It simply says what the mass of solids in solution is, the mass of solutes. And so typically you would dry out that solution, and knowing the initial volume of the solution and then weighing the salts that remain after the solution has been completely dried or evaporated, you can then calculate the total dissolved solids. But total dissolved solids is still, even if it doesn't tell you the specific chemistry, kind of a useful overall parameter for describing water quality. And the things that I'm talking about here don't just pertain to groundwater, they pertain to surface water and even seawater as well. So when we talk about continental waters, typically the total dissolved solids concentration in rain is relatively low, no more than about 10 parts per million. And parts per million is a term that, for dilute solutions at least, basically equates to milligrams per liter. If you assume that 1 liter of water equates to a mass of 1 kilogram, then milligrams per kilogram equates to milligrams per liter. Strictly speaking, mass per mass is parts per million. River water is somewhat more saline, and so total dissolved solids, even so, and I'm using the USA by comparison here, it's a large country that spans a lot of different landscapes. In the USA, river water has total dissolved solids for about half of the country, less than about 230 parts per million. And for 90 of the country, less than about 900 parts per million. When we talk about stream discharge, or for that matter, discharge of groundwater from springs, typically total dissolved solids varies inversely with stream discharge. And what I mean by that is that as the flow rate of the stream increases, the total dissolved solids tend to decrease. And that's typically just a function of dilution. In other words, stream discharge tends to increase as a result of runoff. Runoff is rainfall that runs over the land surface. And although the rain may dissolve some solids, some salts on the land surface, typically it's relatively dilute. So because you're adding relatively dilute water to more concentrated water, as your flow rate goes up with runoff, your total dissolved solids tend to decrease. In terms of groundwater, the total dissolved solids tend to depend on the residence time. And I think I talked a little bit about residence time in my first lecture, but what I mean by that is how long the water resides beneath the surface. And so when I talked about saturation, I was talking about an equilibrium concept, but I also mentioned that one definition of saturation is when the rate of dissolution is equal to the rate of precipitation. And so the kinetics of the reaction, that is the rate of the reaction for any reaction you're talking about in the subsurface, tends to affect total dissolved solids as a function of time, because the longer the time the water is underground, the more elapsed time there is for the water to dissolve solids. So basically, as residence time increases, total dissolved solids increases. Total dissolved solids in groundwater also depend on lithology, that is, the type of rock or sediment you're looking at. So igneous and metamorphic rocks, which typically consist of silicate minerals, tend to have lower total dissolved solids usually, because silicate minerals dissolve relatively slowly. Whereas in sediments or sedimentary rocks, particularly if you're looking, for example, at carbonate rocks, which dissolve more quickly, or rocks with evaporite minerals like halite, or if you were looking at clays where there's the potential for ion exchange, you can have higher total dissolved solids than you would in igneous and metamorphic rocks. So I've shown you this graph before, but I wanted to show it to you again because this illustrates what I'm talking about in terms of TDS varying with discharge. And this is for a karst spring in central Kentucky. And if you recall, I showed the relationship between rainfall or precipitation and discharge, represented by the variable Q in the gray line. And so as rain falls because of runoff, discharge tends to increase. Now, this runoff is directed into the subsurface and comes out at the spring relatively rapidly. And as the discharge increases, the electrical conductivity tends to decrease. And again, that's a dilution effect. And there are a few exceptions here in the wintertime. And again, as I think I mentioned, what can happen in the wintertime is that because of human intervention, basically, because we put salt on the road to melt ice and snow, that runoff can dissolve that salt that is spread on the roads. And so occasionally you'll get an increase as a result of rainfall in the electrical conductivity, which is correlated to the total dissolved solids. The greater the salinity, the easier it is for the water to conduct electricity. So electrical conductivity is correlated to TDS. But usually, except like certain instances in the wintertime where we live, the increased discharge associated with runoff means that electrical conductivity decreases, and that's because total dissolved solids are decreasing. So moving on to talk about the specific elements or compounds that are dissolved in groundwater, we can talk about major and minor solutes. So the major solutes are generally what we also describe as major ions. So they are calcium and sodium and magnesium for the cations, and bicarbonate and sulfate and chloride for the anions. And then you have silicon, which is typically non-ionic. When it dissolves, it tends to be hydrated, so it occurs as a solute that is neutral. It's neither positively nor negatively charged. There are also minor solutes. So the major solutes are typically greater than 5 milligrams per liter each. And which major solute is the dominant solute really depends upon what types of rocks or sediments you're looking at. In terms of the minor solutes, they are typically 0.01 to 10 milligrams per liter. And this really depends on whether the groundwater is oxic or anoxic. So these minor solutes include, for cations, potassium and strontium, and for anions, fluoride and dissolved oxygen, which is non-ionic, it's a dissolved gas. And if the groundwater is oxic, if it has dissolved oxygen, then it typically has nitrate. If it is anoxic, if it does not have dissolved oxygen, then it typically does not have nitrate, but it often has iron. Because as I'll talk about later when I talk about oxidation reduction reactions, when iron 2 is oxidized to iron 3, it becomes very insoluble and it precipitates. Other chemical parameters that we often measure are pH, which is just a measure of acidity, EH, also known as the oxidation reduction potential, which is correlated to dissolved oxygen and to the presence of other solutes like nitrate and iron, as well as specific conductance or electrical conductivity. And specific conductance is just electrical conductivity at a particular reference temperature, typically 25 degrees Celsius, because otherwise electrical conductivity varies with temperature. And these parameters, specific conductance or electrical conductivity, as I mentioned, are related to total dissolved solids. And dissolved oxygen, pH, EH, specific conductance, and temperature are all typically measured in the field. That is, you don't take a sample back to the laboratory and measure it because you know that the temperature will change. And because of the potential for outgassing or ingassing, depending upon whether your sample is sealed or not, that can also affect the pH and the dissolved oxygen and the EH, or the oxidation reduction potential. So typically we want to measure these so-called unstable parameters in the field, but then we will collect a sample and take that sample back to the laboratory to analyze most of these other solutes. And again, feel free to stop me at any point if you have any questions. So we can talk about general classes of reactions or sources of chemicals that control groundwater chemistry. And these include evaporation, because evaporation tends to concentrate solutes. And in extreme cases, that results in soil salinization. And so in places like northeastern Thailand or southeastern Australia, there are places where the water table is close to the land surface and it's a semi-arid or arid climate. Or in the case of northeast Thailand, there are rocks with salt in them, bedded salt that are close to the surface. And so the TDS and the salinity go up as a result of evaporation. There are different types of weathering reactions that dissolve minerals. I'll talk also about adsorption and ion exchange, where clay minerals and metal oxides adsorb ions, usually positive ions, to satisfy structural charge deficiencies or broken bonds on the surface of the mineral. There are redox or oxidation reduction reactions, which typically involve microbially, usually bacterially mediated or catalyzed cycling of metals and nutrients. So, for example, the carbon cycle and the nitrogen cycle include redox reactions. And then finally, contamination is just a really broad category. There are all types of compounds or solutes that can be contaminants. And so I'll talk about certain ones of those. But some of the contaminants that we often focus on are synthetic organic compounds, which are made by humans, like the components of gasoline or chlorinated solvents or pesticides. But there are other types of contaminants as well. And some of them are not even of human origin. They're not anthropogenic. Some of them are naturally occurring, but we call them contaminants because human activity has basically increased their concentration, or even just because they occur at concentrations that cause problems for human and animal and environmental health. So a little bit more about weathering reactions then. The general form of a weathering reaction is where you have a primary mineral or even a secondary mineral. So primary is a rock-forming mineral. For example, like some of the minerals that form basalt, which forms from crystallization of lava. And these minerals react with acids or oxygen to form sediments and dissolved ions. And so one example of a particular type of weathering, a solution weathering, where there is reaction between the water and the rock, is carbonation. And that is the reaction of calcium carbonate with dissolved CO2, which in turn dissociates depending upon the pH to give you a hydrogen ion and a bicarbonate anion. And when that carbonic acid, which is like club soda, basically what gives Coca-Cola acidity, when that carbonic acid reacts with limestone, then it dissolves the calcium carbonate to create a calcium cation and two bicarbonate anions in solution. And this is basically the reaction that creates karst. Then there's a whole class of oxidation reactions and reduction reactions as well. But oxidation is an example of a redox reaction as shown here, where you have an iron mineral like the olivine and basalt that reacts with dissolved oxygen to create a secondary iron oxide or hydroxide. And then finally, in hydrolysis, carbonic acid again reacts with silicate minerals to form clay minerals. So I'll talk about various examples of these different weathering reactions. And note, you may recall from a geology class, if you've had geology previously, chemical weathering is just one type of weathering. There's also physical weathering. Erosion is an example of physical weathering. So water participates in physical weathering, but it also participates in chemical weathering. So this is just as I was talking about, karst as an example of chemical weathering. This is the longest cave system in the world in Mammoth Cave National Park here in the state of Kentucky. And this is the main entrance to Mammoth Cave. And this enormous hole formed over geologic time because of water dissolving the calcium carbonate in the limestone rock. And as I mentioned, these types of karst rocks occur across a lot of the world. The estimate is perhaps 15% of Earth's surface that is not covered by ice. And that includes a number of different areas, including part of Indonesia. In terms of hydrolysis, that is weathering of silicate minerals to form secondary clay minerals, this is an electron photomicrograph. So I don't have a scale bar here, I apologize. But these crystals are on the order of microns. So that is 1/1000th of a millimeter or 1/1,000,000th of a meter. And so you see quartz crystals and kaolinite. Kaolinite is a clay mineral, and clay minerals characteristically have this kind of book shape with individual sheets that look like leaves. So clay minerals are not the only minerals that participate in ion exchange, but they are the main minerals involved in ion exchange. And I should clarify that when we talk about clays, we actually have two different meanings. Clay can refer strictly to the particle size, something less than, I want to say 62.5 microns. I think it's even smaller than that, but basically on the order of 1/100th of a millimeter, so microscopic for an individual crystal. So like the kaolinite that I showed in this preceding slide. But clays are not just a particle size class, they also refer specifically to a category of mineral, and those minerals are typically phyllosilicates. They're typically secondary minerals that involve cations, aluminum and silicon and oxygen and potentially other cations as well. And clay minerals tend to be pretty complicated in terms of their composition, or at least they can be. There are different types of clay minerals. And so what happens is there can be broken bonds on the edges where there may be a residual charge, and the broken bonds tend to result in pH-dependent charge. But there can also be, for some clay minerals, crystal lattices that have defects. So you may be familiar with the term defects with semiconductors, where you're talking about silicon and you're doping silicon compounds to basically compensate for atom of a particular element substituting. Well, that happens in clay minerals as well. And if you have cation substitution in the crystal lattice such that a less charged cation, like +3, like iron, substitutes for a higher charged cation, like silicon, then that results in what we call a structural charge deficiency or a defect. And so in order to maintain electrical neutrality, because electrical neutrality has to be maintained in solution, ions, typically cations, are absorbed into the what's called interlayer between the sheets, like the sheets I showed you for the kaolinite, into space between those sheets. The cations are absorbed out of solution, out of the water, to make up for the charge deficiency. So cation exchange involves the desorption of one type of cation accompanied by the adsorption of another. So the example that I showed here is calcium being adsorbed onto a clay that has sodium already adsorbed. And so in effect, the calcium, because it is a +2 charge, kicks off 2 of the sodiums and replaces them because you're maintaining electrical neutrality. In this particular reaction, calcium being adsorbed onto a clay that initially has sodium is actually what we have in water softeners. I don't know how common water softeners are in developing countries like Indonesia, but we use them in the United States when we have so-called hard water. If we have water that has high levels of calcium, that's not toxic, but it can make it difficult for detergent to work effectively. And you can get buildup of what's called lime on your shower or in your sink. And so some people have water softeners that they pass their water through before the water goes to the tap in order to remove the calcium and replace it with something else. In this example, sodium. Clay minerals tend to have greater affinity for, that is, they're more prone to adsorb divalent cations because the charge to mass ratio is greater for a divalent cation like calcium than it is for a monovalent cation like sodium. But really, whether this reaction goes to the right, as written above, calcium adsorbs onto sodium and then the sodium desorbs, or whether it goes to the left, the sodium adsorbs and the calcium desorbs, really depends upon the composition of the groundwater. So if you have, for example, clay with calcium and you immerse it in seawater, that calcium will desorb and sodium from the seawater will adsorb until you reach an equilibrium. So it depends upon not just the composition of the clay, but the composition of the water itself. So this is a molecular diagram here from Grimm, who was a well-known clay scientist in the United States, showing the structure of the phyllosilicate mineral smectite. And this is what we call a dioctahedral or 2-to-1 layer clay mineral, where for each individual crystal, you have silicon tetrahedra, where you have 4 oxygens with a silicon atom in the middle, and these tetrahedra are linked in a sheet. And so you have a top tetrahedral sheet and, or in this case, bottom rather, and then a top tetrahedral sheet. And in between the two, you have aluminum octahedra, where you have 1 aluminum and then 6 oxygens around the aluminum, or rather 6 hydroxyls rather around the aluminum. And let me make sure I'm saying this right. These are oxygens around the aluminum. Sorry, I'm tripping over my words. Anyway, you can see here this Si4 - X ALX. That reflects the fact that in some instances, the aluminum, which is +3, will substitute for silicon in the top or the bottom sheet, which is +4. And that's where you get a residual negative charge, and calcium or sodium in this case, could also be magnesium or potassium or another cation, gets adsorbed along with water into this inner layer. And so that's why smectite clays vertisols tend to shrink and swell depending upon the water content as well. So it's not just the cations, it's actually water around the cations that goes into the layers between these molecules. And so again, you can see this is a really tight, really microscopic scale here. Clay minerals, not simply clay minerals, but clay-sized minerals, metal oxides, for example, can also adsorb ions onto their surfaces. And so this is an example of how that happens. And depending upon the pH, the surface may be positively charged or negatively charged. And as it says here, metal atoms near the surface tend to coordinate with hydroxyl groups. So you have positively charged atoms, cations, adsorbing onto the negative bonds at the surface. In terms of oxidation reduction reactions, or redox for short, these involve electron transfer, and they can occur without microorganisms, but the rate is much slower without microorganisms. So basically, bacteria usually, sometimes archaea, like methanogens, catalyze these reactions enzymatically. And so what this involves is elements changing their oxidation state. So their oxidation state basically has to do with the number of electrons. And so elements that have multiple oxidation states can act as reductants. That means they lose an electron, or oxidants, which means they gain an electron. And so we have an expression in English in chemistry classes, Leo goes Ger, which is a way to remember because Leo is a word for lion, and a lion makes a grr sound. So LEO is lose electron oxidation, GER, gain electron reduction. So again, shown here, the electron loss is oxidation. So in this case, iron 2 is losing an electron, so it becomes iron 3. Going the other way, if iron 3 gains an electron, it becomes iron 2. So lose electron, LEO, oxidation, gain electron, GER, reduction. To maintain electrical neutrality in solution, you have to couple the oxidation of one solute to the reduction of another. So in fact, these electrons don't accumulate in solution, they're just being swapped back and forth. And even though solution can conduct electricity because you have positively charged cations, negatively charged anions, overall electrical neutrality is maintained in solution. So I mentioned EH previously. It's just the measured electron potential for an electrochemical cell. And you can calculate something called PE, which is analogous to pH. If you remember the definition of pH, that's the negative base 10 logarithm of the hydrogen ion concentration or hydrogen ion activity. PE is just analogous to that. It's the negative base 10 logarithm of the electron concentration. That's not really a measured property, it's a calculated property. EH is the measured property. I'll talk more about EH down here at the bottom of the slide, but in the meantime, I want to reiterate what I said previously, is that in contrast to precipitation and dissolution reactions or to ion exchange reactions, redox reactions, oxidation reduction reactions usually are not at equilibrium. So for example, that's why you had a carbon cycle or a nitrogen cycle. Typically, because the equilibrium constants are large, they're irreversible. So if you think of the carbon cycle, this is an example of oxidation or respiration. That is organic matter written in shorthand form, CH2O, carbohydrate. If you multiplied this by 6, it would be C6H12, rather, O6, which is glucose. So you're reacting dissolved oxygen with something like glucose, with some form of organic matter, and it produces carbon dioxide plus water. Well, the reverse reaction to that is just photosynthesis, that water plus carbon dioxide plus sunlight in plants generates oxygen and biomass, or CH2O. But photosynthesis doesn't just flip the switch on respiration. Basically, you have the entire carbon cycle going from respiration through photosynthesis and coming back again, but it's not a forward-backward reaction. So that's why we don't use an equal sign. Whereas, I think when I showed sodium chloride dissolving previously, I wrote it as NaCl equals Na plus Cl, equals meaning it can go one way or the other. So back to EH, the values of EH or PE are constant when you have one redox couple, that is one particular element that is dominating the others. So going back to the previous slide, if iron is your dominant redox couple, iron reduction or iron oxidation, then that's going to regulate the EH value. But otherwise, electrons are going to be generated and consumed by multiple different redox reactions. So just like TDS represents the combination of a bunch of different reactions, EH can also represent the combination of a bunch of different reactions. Typically, if you have oxic conditions, if you have detectable dissolved oxygen, because the reaction, basically the reduction of dissolved oxygen to water is the dominant couple, EH is a reasonable measure of the oxidation state. EH is also a reasonable measure of the oxidation state for iron reduction. But in systems where there are other reactions occurring, EH doesn't work as well in terms of describing the redox state of the system. So finally, there's something called the redox ladder. And from thermodynamic considerations, what this says is that you can define an electrochemical evolution sequence. And this goes from increasing or the highest energy generated to the lowest energy generated. So this sequence basically goes from reduction of dissolved oxygen to water through reduction of nitrate to nitrogen gas or denitrification. So this is basically the first anoxic reaction. Then dissimilatory nitrate reduction, which is reduction of nitrate to ammonium. And then you start to get into metal reduction, reduction of manganese 4 to manganese 2, reduction of iron 3 to iron 2, reduction of sulfate to sulfide, and finally methanogenesis. There are a couple of different methanogenesis pathways, but the one that I've shown here is reduction of bicarbonate to methane. And with the exception of methanogenesis, all these other reactions are catalyzed by bacteria. Methanogenesis is catalyzed by archaea, a different kingdom of microorganisms. But basically, because there's not a lot of bioavailable carbon in aquifers, as you progress along a flow sequence within a confined aquifer, as I show later, as you're moving farther and farther along the flow path, and presumably you're farther and farther away from the recharge zone, from fresh water coming in generating more oxygen, then you tend to see a progression, maybe not all of these in sequence, but you go from oxic to nitrate reducing to metal reducing to sulfate reducing, and finally you get down to methanogenic. And depending upon what the lithology, what the mineralogic composition is, you may not go all the way through this sequence. You may go only as far as metal reducing. So I'll show an example of that later. All right, so then getting back to what I mentioned previously, how do we define pollution, or how do we define contamination? And I would just define it, and this is kind of my own definition, but I think it's fairly common, that it's just the occurrence of a substance in harmful or undesirable amounts. And this is true for air pollution, this is true for surface water pollution. Of course, we're going to be focusing on groundwater. Really, we can say also that pollution depends on the intended use, such as for drinking water. So, for example, you might not want to drink water that you're irrigating your rice with, but it may be sufficient for agriculture. So pollution in part depends on the intended use. And it doesn't necessarily involve human health impacts. It can involve ecosystem impacts or even agro-ecosystem impacts. So if you have elevated salinity, at some point, not only is the water not drinkable by humans or animals, but it also kills plants. And finally, as I said, and there's some debate about this point. Some people say pollution or contamination has to result from human activity, but increasingly there's a group of us who would argue, yeah, you can have water that you consider naturally polluted because you have some substance that's naturally occurring that exists in harmful, undesirable amounts. So we can classify chemical pollutants in different ways. First, inorganics. So we have metals and metalloids, mercury, cadmium, lead, arsenic, chromium as examples. Some of these occur as organometallic compounds or ions in solution. I've listed these 5 in particular because they are particularly toxic to humans. And of these, arsenic in particular, in a lot of the world, is naturally occurring. There are also radionuclides. For example, radioisotopes of uranium, thorium, plutonium, cesium, iodine. There is naturally occurring radioactivity, but obviously human activities have contributed to radionuclide contamination as well. These first 4 are all metals. They're cationic. Iodine occurs as an anion. Some of these have multiple different radioisotopes, for example, uranium and thorium, and I think plutonium. Really, also different radioisotopes can emit different types of radiation, alpha, beta, or gamma, which can have different human health impacts. I mentioned nitrate. Nitrate occurs naturally, but it also is a pollutant commonly associated with human or animal waste, like leaking sewers or application of animal manure as fertilizer or inorganic fertilizer. And finally, salt can be considered a pollutant. And of course, saltwater intrusion in coastal aquifers is an example of that, but there can also be salt contamination inland. And I showed the example of road salt being used to melt ice on highways in cold regions like Kentucky in the winter. I mentioned also organic pollutants, and we pay a lot of attention to these because they tend to have human health impacts at really low concentrations, as noted down here. And so typically we're talking about synthetic compounds. And these include volatile organic compounds, or VOCs for short, such as the components of gasoline, benzene, ethylbenzene, toluene, and the isomers of xylene. Also chlorinated solvents, such as chlorinated methane compounds, chlorinated ethanes and ethines. These are created by substituting, for example, in the case of methane, chlorine for hydrogen through synthetic processes. So if you go from CH4 to CCl4, that is carbon tetrachloride or tetrachloromethane, which is a common solvent. There are also semi-volatile organic compounds. They tend to be higher molecular weight and more complicated chemical structures, often multiple benzene rings. These include things like polychlorinated biphenyls, polycyclic aromatic hydrocarbons. Those are examples of the multiple benzene rings, as well as pesticides. And pesticide is not a chemical term. Pesticide indicates that it kills pests. So there are all different types of compositions of pesticides, but many of them are semi-volatile, just meaning they have a low vapor pressure. And then finally, in recent years, the last 20 or so, we've become much more aware of what we call personal care products, pharmaceuticals like birth control compounds or anti-seizure medications, or illicit drugs even, but also antimicrobials like antibacterial soap contains triclosan. And that may not be toxic to humans, but it can have an effect on the microbial ecology of the environment such that microorganisms, basically pathogenic microbes, evolve to evade antimicrobial activities. So excess use of antimicrobials can cause the emergence of so-called superbugs. So again, part of the reason we care particularly about synthetic organic compounds is they can have human health effects, birth defects, or other toxic effects They may be carcinogenic, causing cancer at concentrations of parts per million or even parts per billion. So I asked this sort of rhetorical question here. We say in English, oil and water don't mix very well. Typically, that's because organic compounds are nonpolar and water is polar. So what happens when, for example, gasoline is spilled at a gasoline filling station? If it leaks into the subsurface, if it percolates to the water table, often you will have residual gasoline, that is mixtures of different organic compounds, as a non-aqueous phase liquid. These are relatively insoluble. It doesn't mean it doesn't dissolve at all. It just means the solubility is relatively low. And they can be more or less dense than water. So dense NAPLs, dense non-aqueous phase liquids, or what we call DNAPLs, are like some of the solvents, like I mentioned, carbon tetrachloride or trichloroethylene or tetrachloroethylene. And they tend to have greater density than water, so they tend to sink beneath the water table. Light non-aqueous phase liquids, like the components of gasoline, tend to have density less than water. They tend to be floaters, as we call them, because you have residual, what is called free product, floating on the water table. And so I'm not really going to talk about remediation of contamination here. I don't have enough time. But basically, if the compound is floating on the water table, it is easier to clean up. Also, the components of gasoline tend to volatilize. They have high vapor pressure. And so it's not simply a matter or simply an alternative of pumping the floating gasoline off the water table. You can also potentially induce volatilization through what's called vapor extraction. So the light non-aqueous phase liquids tend to be easier to clean up. And then just this question at the bottom, why do we worry about compounds that don't dissolve much, that have a low solubility? I'll go back to the previous slide. It's just that even at very low concentrations, they can be relatively toxic. And I'll show an example of that later. So let me talk a little bit then about sources of contamination. These include what we call point sources, such as septic tanks for human waste. Latrines are an analog to that. Leaking underground storage tanks, such as gasoline stations. Wastewater outfalls. Even treated wastewater may have elevated levels of pollutants, even after treatment, say coming from a municipal sewage treatment plant. And chemical spills. So if you have a tanker truck crashing on the highway. And then there are non-point sources, which are more diffuse and therefore more difficult to clean up. And these include runoff from farms and urban areas, atmospheric deposition, if you have pollutants that dissolve in rainfall and fall to land surface and then infiltrate. Geogenic sources of pollution, I mentioned arsenic as an example of that, and seawater intrusion. So I've been talking for almost 50 minutes. Let me pause for a moment and see if there are any questions. Okay, I'm seeing a question in the chat. Microplastic contamination. Judfun, that depends, because microplastics can become so small that they are almost like colloids. That is, they are microscopic, and some of them actually can partially dissolve. So I typically don't think of microplastics as contributing to TDS because technically they're not dissolved. They would be considered part of TSS, or total suspended solids. So I've been talking mainly about dissolved compounds, but microplastics are certainly pollutants. They're primarily in surface water, but in areas where you can have large pore spaces, you can also have microplastics in groundwater, like in karst drains. Another example of a suspended pollutant that I haven't really talked about is microorganisms in general. So I've talked about bacteria catalyzing redox reactions, but obviously also there are bacteria that are pathogens. and viruses and protozoa. And that's an entire other category of pollutants that I decided not to talk about tonight because they're not really chemical pollutants, they're biological pollutants, but they are still pollutants. And in fact, they are some of the most serious pollutants in terms of human health impacts. Again, particularly in developing countries where sanitation may be problematic. Any other questions at this point? Okay, this is a cartoon from one of the introductory textbooks that I used to use. And this shows an example of contamination by dense non-aqueous phase liquids, or DNAPLs, and light non-aqueous phase liquids. So to the left is a scenario where there's a factory and maybe there were drums filled with trichloroethylene or trichloroethene. Sometimes we write it with the YL, sometimes we just leave the YL out. But basically, this is where you have a carbon-carbon double bond. And in the case of ethene or ethylene, there are 4 hydrogens. With trichloroethene, 3 of those hydrogens are replaced by chlorines. And that makes it a really good solvent, but it also is carcinogenic and potentially causes birth defects. So because TCE is a non-aqueous phase liquid, it leaks and goes down to the water table, and some of the TCE will dissolve and move in the direction of groundwater flow and create what we call a contaminant plume, called a plume because it's kind of shaped like a feather. It's elongated and rounded. But some of it will also continue to stay as a separate phase, and it may actually follow the bedrock topography if you have a permeable layer overlying a relatively impermeable layer. And you can also have little blobs of TCE in the saturated zone, but also in the unsaturated zone. So this becomes a 3 fluid phase system. You have water, you have air, and then you have the chlorinated solvent existing as a separate liquid phase. To the right is a scenario where there is a leaking underground storage tank at a gasoline station, and the gasoline moves down again to the water table, but tends to float on the water table. Some of it will dissolve. Some of it will volatilize, as I mentioned. And again, you may have residual gasoline left as little blobs, discontinuous little pockets of gasoline within pore space in the Redox zone. One thing to note here that I tell my students is where you have a basement, if you have gasoline vapors intruding into the basement, that can be very dangerous, not only because the vapors can be toxic to breathe, but also they can combust. And so if you have, for example, a gas-powered water heater powered by natural gas in the basement, the house could explode because the pilot light may combust the gasoline vapors. So groundwater pollution is not always just a water pollution problem. It can also be an air pollution problem as well if you have volatile organic compounds. So moving on, let me talk a little bit about stable isotopes of water, because there was a question, particularly last time, about isotopes. When I talked about different types of chemical pollutants, and I mentioned radioisotopes. Radioisotopes are different from stable isotopes because they decay. An isotope is basically a version of an element with a particular number of neutrons. And if you have basically 1 or 2 extra neutrons, that element will often be a less common stable isotope. That is, it doesn't decay, but sometimes, especially if you have more than 2 or even 2, it can be a radioisotope. So for example, let's talk about hydrogen. Hydrogen 1 is the most common version. That is, you've got 1 neutron. Hydrogen 2 or deuterium is a stable isotope. Hydrogen 3 is tritium. That's a radioisotope. Likewise with carbon, carbon 12 is the stable form of carbon. And in each case, the lowest mass is the most dominant one. And then carbon 13 is also stable, but is less common. And then carbon 14 is a radioisotope. So in particular, hydrologists use stable isotopes of water, oxygen 18, where the common stable isotope is oxygen 16, and hydrogen 2, or deuterium, sometimes just abbreviated capital D, where hydrogen 1 is the dominant stable form. And so looking at the relative abundance of oxygen 18 compared to oxygen 16 and hydrogen 2 compared to hydrogen 1, those differences have been used to delineate or identify the sources of precipitation and the timing of precipitation. They've been used to identify the effects of evaporation, because evaporation, as I'll show in a minute, preferentially selects for the light stable isotope to go into the vapor phase and the heavier stable isotope to remain in the liquid phase. And also, just if you have different end members mixing, if the end members have distinct stable isotope compositions, then you can do unmixing calculations and identify the relative contributions of the different end members. There are different types of fractionation of the stable isotopes. They can be either equilibrium fractionation or kinetic fractionation. But basically, relative to the light stable isotope, the heavy stable isotopes in water tend to be preferentially enriched in liquid water, as I mentioned, and depleted in the water vapor. And as an example, evaporation preferentially enriches oxygen 18 relative to oxygen 16 and hydrogen 2 relative to hydrogen 1, but it also enriches oxygen 18 relative to hydrogen 2, because hydrogen 2 is a lighter atom than oxygen 18 is. So the oxygen 18 is more likely to be left in the liquid phase than the hydrogen 2 is. So this cartoon I like, this is from the University of Texas. And it just shows how isotopic enrichment occurs through fractionation. The lighter isotope tends to evaporate first. And that's not to say that it's all oxygen 16 going into the atmosphere. It's just the proportion of oxygen 16 in the atmosphere is greater than the proportion of oxygen 18. And conversely, when you have precipitation, the oxygen 18 tends to go into the condensed phase more and rain out relative to the oxygen 16. And the same thing happens with deuterium also, that you have more deuterium left in the liquid phase than you do in the gas phase. It was realized about 60 years ago, actually, that the relative abundances of oxygen 18 and deuterium co-varied. And typically we describe the relative abundance of any stable isotope compared to its more common baseline version by what we call a delta notation. And this is in parts per thousand relative to a standard, in this case, standard mean ocean water. And so using this delta notation, the relative concentration of oxygen 18, the relative abundance, or the relative abundance of deuterium and precipitation can be related. They co-vary. And this was identified at a global scale by Craig initially, using what's called the global meteoric waterline, basically looking at isotope data from rainfall all over the world. He found that they co-varied neatly. But that global meteoric waterline is basically the combination of a bunch of regional or local meteoric waterlines. I mentioned that oxygen 18 and deuterium can be used to fingerprint the timing and sources of precipitation. And that's in part because the progressive depletion, what's called the Rayleigh distillation of oxygen 18 and deuterium in precipitation, results from rain out during storms. So initially, you have the heavier isotopes being rained out, and the longer it rains, the so-called lighter the rainfall gets. That is, less heavy isotopes, more light isotopes. Also with increasing elevation, because again, you tend to rain out as you go up in elevation. And finally, with distance from the coast in mid-latitude regions, like in Asia or Africa or the Americas, air masses often originate over the ocean as they move inland and rain occurs. The farther the air mass goes, the lighter, that is, the less O18 or the less deuterium is going to be left in the residual water vapor. So this is the global meteoric waterline of Craig. This is one of the most cited papers in isotope hydrology, and he just showed that the relative abundance of deuterium equals roughly 8 times the relative abundance of oxygen 18 plus 10. So you have pretty much a linear relationship here. And it can diverge a little bit where you have really enriched values. These closed basins tend to be affected more by evaporation. And this is shown a little bit more in this paper here, showing the relationship between deuterium and oxygen 18 abundances, where this is the global meteoric waterline. And if your water is referenced to this initial point here, that in the wintertime, because the air is cooler, or as you move to higher latitude, as you go farther inland in the continents, like in North America, or as you go higher altitude, you move farther down the meteoric waterline. Both deuterium and oxygen 18 abundances tend to become lower. As you conversely become warmer or move to lower latitude or lower altitude or in coastal regions, you move up the global meteoric waterline. You diverge from the global meteoric waterline along a trend with a subparallel slope where you have evaporation, because I remember I said evaporation tends to preferentially concentrate oxygen 18 relative to deuterium. So if you've got this subparallel slope compared to the global meteoric waterline, you can say, oh, that's indicative of an evaporation signal. Transpiration doesn't tend to fractionate as much. Plants don't really fractionate water molecules very much. So if you see an evaporation trend like this, and if you extend that trend back to the meteoric waterline, you should get a composition that's what you would expect for the rainfall initially. So of course, when water hits the ground and as it infiltrates, it's subject to evaporation to some extent. Obviously, it's only partial evaporation, or else there wouldn't be recharge. So recharge tends to be slightly modified by evaporation. The extent to which it is modified depends on parameters like the relative humidity and temperature, as well as just the residence time of water in the soil zone. The longer the water stays there, the more the water is going to evaporate, the more residual water is going to be isotopically enriched. As I mentioned, in terms of mixing, different recharge sources can be isotopically distinct. So if you've got waters coming from a local flow system mixing with waters coming from a deep flow system in a discharge zone, you may have an isotopic composition that is in between those two end members. And finally, even though oxygen 18 and deuterium are stable isotopes, they're not radioisotopes, so you can't use them specifically for dating. They're useful for capturing, for relative dating rather than absolute dating, for capturing hydrologic signals at different time scales because of the dependency of isotopic compositions on parameters like temperature. If you're looking at deep regional aquifers with time scales of tens of thousands of years in Europe, Northern Europe, or in North America, you can actually see variations in O18 and deuterium over glacial and interglacial timescales. In shallower aquifers, you can see seasonality of recharge, because if you go back to this graph, you can see that winter tends to be isotopically depleted and summer tends to be isotopically enriched. And then where you've got basins with rapid circulation, like karst basins, you can even see event scale variability in stable isotopes. So that brings me to my case studies. The first is a study of a deep regional aquifer system. This is the Wilcox Aquifer, the Wilcox Group in the Gulf Coastal Plain of the United States. And this aquifer is a confined aquifer. Recharge occurs along the margin of what's called the Mississippi embayment, kind of an upland area. It's possible that there is some recharge away from the margin by downward cross-formational leakage, but numerical modeling indicates there's not much. There is a superficial unconfined aquifer, and then beneath that, a confined aquifer. The Wilcox is the second confined aquifer. And so because it is deeper than these other two, it is not pumped as much. Whereas particularly the Mississippi Valley alluvium is used a lot for irrigation. And so the study area is the southeastern part of the state of Missouri and the northeastern part of the state of Arkansas, west of the Mississippi River and east of the St. Francis River. So this is a location map relative to the United States, and both case studies are within this region. The first case study is the western half of this rectangle, basically, whereas the second case study is kind of the northeastern quarter, maybe, of this rectangle. So this is Missouri, this is Arkansas. Later, I'm going to be talking about Kentucky, which is the state that I'm in. I'm here in Lexington, in the northeast central part of the state. But the second case study I'm going to be talking about is in the western part of the state. So for reference, here's Canada, here's Mexico, there's New York, there's Washington, there's Los Angeles. And this is from a study that was done for the PhD research of one of my students, Stefanos Haile. And this is just a map showing the major superficial aquifers. This is the Gulf Coastal Plain, and this is the limit of the Gulf Coastal Plain. So this represents the shoreline of the Gulf of Mexico at some time in the geologic past, starting 65 million years or so ago. So the study area for the first study that I'm talking about is basically where I'm outlining this oval with my cursor. And then the study area for the second part is right up here. So looking further at the Gulf Coastal Plain and the Wilcox, these contours are in feet above sea level. So basically multiply by 0.3 to get meters, but you can see the trends that east of the Mississippi River, which forms the boundary between Missouri and Kentucky and Tennessee, and Mississippi to the east, Missouri and Arkansas and Louisiana to the west. It's topographically asymmetric. So there are bluffs and it's relatively steep to the east, hilly, not mountainous, but to the west, it's relatively flat. So the Mississippi River floodplain is more to the west, and the river itself is kind of up against the valley wall to the east. So what that means in terms of groundwater flow is that following the topography, east of the river, flow tends to be toward the west, whereas west of the river, flow tends to be more toward the south, parallel to the river. And so you can see to the right, this transect here going north, northeast to south, southwest, parallel to the river, but west of it. And each of these dots or symbols, the red dot, the blue diamond, the green triangle, represents a well that we sampled. Most of these wells are in the Wilcox Aquifer. Some of them are in the overlying Claiborne Aquifer, and one is in the underlying McNary Aquifer. And then we also had core samples taken from these three sites with the inverted triangles. And basically the Wilcox dips going south toward the Gulf of Mexico. So you can see it in this slide here, where the alluvial aquifer is shown at the top, and then basically the white represents aquifers, the gray represents extensive clay units, and each of these vertical lines represents a well. And as you'll see in the previous diagram, these wells are projected onto this line of cross section for reference. And so you have the upper Claiborne Aquifer here, and then an extensive confining unit in the middle Claiborne Aquifer, and then below the middle and lower Wilcox Aquifer. And so these confining units tend to isolate the superficial aquifer from the deeper aquifers. So what we found in terms of results is that we saw trends along the hydraulic gradient. This is along a distance of about 300 kilometers, basically north to south, that the wells got deeper. That was evident in the previous diagram. So the well depth increased from about 116 to about 518 meters below land surface. Temperature increased, that's just following the geothermal gradient. pH increased, which is indicative of progressive water-rock interaction. Basically, it's a system that's buffered, pH is buffered by reactions with the sediment. The major ion composition evolved. It was bicarbonate dominated, but it started out calcium dominated near the recharge zone and became sodium dominated. The groundwater was anoxic for all of the wells. Dissolved oxygen was detectable, but we think it was kind of an artifact of oxygen diffusing through our sampling tubing. For example, it was low, less than 1 milligram per liter. Nitrate was undetectable in virtually all the wells. And iron 2 was detectable in about 2/3 of the wells. We also saw progressive decreases in sulfate and increases in methane down the flow path. So this is what you would expect with that electrochemical evolution sequence. You go from oxygen to nitrate to iron to sulfate to methane. Basically oxygen reduction, nitrate reduction, iron 3 to iron 2, sulfate to sulfide, and then bicarbonate methanogenesis. And so overall, carbonate dissolution and precipitation perhaps, cation exchange, which explains going from calcium dominated to sodium dominated, and the redox reactions appear to control the water chemistry. So this is basically, if you think of it from a chemical engineering perspective, like a reactor column. As the water is passing down gradient, the chemistry is evolving. And the water isotopes show that there was limited evaporation during recharge. So this is a semi-log graph, basically calcium in millimolar on the y-axis and the distance in kilometers on the x-axis. Focus on the Wilcox, in particular, the circles, and you can see a nice decrease in the calcium and conversely, an increase in sodium. In terms of iron, this is an arithmetic plot, but you can see that iron increases some distance down the flow path and then drops off. And this is a photograph from an aeration basin for a municipal water treatment plant. These are almost all municipal wells, small town wells. Near Caruthersville, Missouri, they are aerating the water to get the iron out. Iron's not toxic. It just makes the water taste like you've got blood in your mouth, and it stains your clothes and stains your dishes. So people don't like iron. It's what we call an aesthetic contaminant. So this is in a part of the flow system that has relatively high iron. You can see this kind of stain around the concrete, sort of like a bathtub ring. Sulfate, you can see a really nice decrease in sulfate down the flow path. Again, arithmetic plot. And what's happening here is that the iron 2 and the sulfate that is being reduced to sulfide are precipitating to form pyrite as a secondary mineral, pyrite cement. And it's cementing together grains of things like siderite, which is an iron carbonate mineral, and quartz. And then finally, methane, another logarithmic plot. You can see a gradual increase in methane down the flow path. And in terms of the stable isotopes of water, you can see that deuterium and oxygen 18, and these are values not just from our study, basically the circles, but also from other studies in the area, that they tend to fall along the local meteoric water line, which is parallel to the global meteoric water line. And let me get to Rama's question in just a second. So anyway, you can see these generally don't deviate much from what you would expect for rainwater. In fact, we have a volume-weighted average composition of rainwater from near the upgradient part of the flow path that falls right on this plot. So, Raman, thanks for your questions. Let me get to those now. So in terms of the parameters that control groundwater chemistry, which one has the most important effect? I would say it depends on where you are, but particularly in a tropical environment like on Java, I would say probably weathering is most important, at least in terms of controlling the chemistry. It depends on how you define important. If you talk about it in terms of water quality, in terms of whether water is suitable for human use or for agriculture, contamination may have the most important effect. And so you'd expect to see contamination being significant in urban settings or in agricultural settings. And how far is the negative impact of these parameters are degraded? Like I said, if you have elevated levels of arsenic, even if it's naturally occurring, that can potentially cause, I don't know what the statistic is for West Bengal state and India and Bangladesh, but I know that 50 million people are potentially exposed to elevated concentrations of arsenic. I don't know what the toxicity is, but you can also just think of the human health burden, even if people don't die. Okay, in my research, if I take samples with multiple limitations, what's the minimum limit I should set? I want to answer that question and not avoid it, but I would say, I guess it depends upon what questions you are trying to answer. In other words, how good is your spatial coverage? You know, if you have a relatively small basin and you want to evaluate how water quality changes over a scale of kilometers, you know, maybe just 10 wells or fewer will be sufficient, particularly if it's relatively homogeneous. But if it's relatively heterogeneous, or if you have a larger basin, then you're going to need more samples. Also, one of the assumptions we commonly make in groundwater is that the concentrations, the composition doesn't change much with time. But in karst systems, for example, we know there can be relatively rapid circulation. And so, for example, you might have greater potential for contamination after a storm. Even though I said storms typically introduce more dilute water, if that storm water is carrying microorganisms, then that's more of a concern. So how many samples means not just how many locations, but potentially how often as well. And then there's the related question of how many different things you should be sampling for. And so one of the critical lessons that was learned in Bangladesh with the arsenic crisis in the late 1990s and early 2000s is that the British Geological Survey, which was doing work through the Department for Foreign Development in Britain, helping out the Bangladeshis in terms of drilling water wells so they could avoid contaminated surface water. They analyzed for a bunch of different things, but they didn't think to analyze for arsenic. And then people started turning up with symptoms of arsenic toxicity. So in terms of how many different things you should analyze for, basically, again, it depends in part upon what you're interested in, but it's easier to analyze for more things and then realize that some of those things are not present than it is to analyze for fewer and then say, oh, wow, I wish I'd thought to analyze for this other thing also. Rama, does that answer your questions?
Mr. Rama, it already answered your question.
Yeah, thank you very much, Prof. Alam. It's very nice to know how you can there's this my research. Thank you, Prof. Alan.
You're welcome. I mean, it's not an exact answer. I can't say like 3 or 9. It kind of depends upon what questions you're trying to answer and where you are.
Yeah, maybe
as well as how much money you have.
Yeah,
you know,
it's very, very expensive to this groundwater.
Drilling wells can be expensive, analyzing samples can be expensive. And so, you know, that's why it's important to try to pick the wells that give you the most information.
Yes, thank you very much.
I understand. You're welcome. Okay, so let me go on and I'll finish then, and then I'll see if there are any other questions. We're talking about my contamination study. So as I mentioned, this is in the same general region of the United States, but it's at the northern limit of the Gulf Coastal Plain. And this is a study that also ties into some of the work that I was doing on groundwater stream interactions. This was a nuclear facility. It produced nuclear fuel, enriched uranium for power production for about 60 years. And like a lot of industrial facilities in the United States, it used an organic solvent, in this case trichloroethene, as a degreaser, you know, just to clean parts, machine parts and things like that. It used a lot of it. And also, and much less common, there was technetium-99. Technetium is is an element that's a transition metal. It's in the same column of the periodic table as manganese and rhenium. And technetium-99 is a beta emitter that has a long half-life. I think I should remember, 200,000 years, I believe, roughly. And this was a byproduct of uranium reprocessing. Well, in 1998, there was a study just analyzing private wells that belonged to rural residents who lived close to this plant. And these contaminants were detected, and then the government was like, uh-oh. And ultimately, this facility was put on what we call the National Priorities List, or the Superfund list, meaning it was one of the most serious contaminated sites in the United States. And what was found was that these plumes, remember I said a plume is called that because it's kind of feather shaped, but these long, elongated kind of bodies of contaminated water were mapped in what's called the regional gravel aquifer. It's not really regional, it's more local. But these plumes were several kilometers long and extended all the way from this facility out to the Ohio River. And so this is a map of what the TCE plumes looked like as of about 2010. And they're color-coded by concentration. So the cooler the color, the lower the concentration. Remember I said that even though organic compounds, non-polar organics, don't dissolve much, they can dissolve enough to pose health risks. Well, based upon human health studies, our drinking water standard is 5 micrograms per liter, or 5 parts per billion. And you can see that there were concentrations greater than 100,000 micrograms per liter. So 20,000 times the drinking water standard in the source zone. Now, this is indicative of probably some residual dense non-aqueous phase liquid, but there was even elevated concentration of TCE out in the far part of this plume. You actually have 2 plumes. There's a groundwater divide here. And this farther north plume, called the northwest plume, basically discharged partly via springs into a creek. So let me look at the rest of the chat here. So this is Putu's future research related to the use of isotopes in groundwater and surface water. Let me get to that in just a minute if I can, Putu. I'm going to wrap this up. So this is the map of the TCE plumes, and then the technetium plumes were smaller, but still significant. So what we found, what I and my students found when we started looking, was that there were springs in this stream that was a tributary to the Ohio River that ran off-site that carried processed water. The water that was discharged into the creek was really cooling water for this plant. It wasn't particularly contaminated. The contamination occurred basically with compounds that were in the soil, and infiltration dissolved those contaminants and carried them to the water table. And then that groundwater flowed toward the Ohio River. And some of that contamination came out, as we said, sort of short-circuited up into this stream before it hit the Ohio River. Because if the plumes hit the river, then a lot of that contamination is just going to be diluted. And these springs, this is not a karst terrain. This is basically clays and silts and sands and gravels, but some of the clays were fractured, perhaps because of faulting in the area. And in addition, the stream was channelized, was dredged in the early 1950s, and that may have also enhanced the occurrence of the springs. So this is another hydrostratigraphic cross-section, but instead of the scale I showed previously, where it was like 300 kilometers long, this is like less than that, probably 6 kilometers from the plant out to the Ohio River. And this white layer here is the main contaminated aquifer. And I showed this slide previously. This is my student, Ovijit Mukherjee, gauging along the river. We were looking at changes in discharge, basically at seepage inflows coming into the creek, to look at where contamination might be coming in as well. And so we found, this was a set of several different studies over about a 12-year period, that even though these springs were in sediment, they weren't in rock. They didn't really move around that much. They tended to persist, their locations persisted. Now, the flow varied, but the variation really was just a reflection of the water table going up and down seasonally. Redox reactions can also affect chlorinated organic compounds. And under some circumstances, under anoxic conditions, you can get biodegradation, that is reduction of trichloroethylene to a non-toxic byproduct. But in this case, we didn't really see that because the residence time was short. Water was moving quickly through the system, and there wasn't that much absorption of the contaminants onto the minerals. Finally, what we found was that the concentrations went down over time, but it's because the plant operator put in wells up the flow path to pump out the contaminants. They put in extraction wells. So this is a photograph of the biggest of the springs, what we call WB3. That's what it looked like in August 2002. That's what it looked like in October 2010. So the orifice kind of evolved because of soil piping, but it still persisted in about the same location. I showed this slide before in the last talk about using thermal probing to identify sites of groundwater inflow, and these coincided with places where we saw springs that we sampled for contaminants. And then finally, and this is my last slide, this is the trend in squares for the TCE from 3 different studies and in diamonds for the technetium over time. And you can see the concentrations dropped off. And that's because the contaminated groundwater was being pumped out. So they didn't get all of the contamination, but much of the contamination was removed before it got to the springs. So let me go back to Putu's question first and then David's question. So stable isotopes, what do I think of future research related to the use of isotopes in groundwater and surface water? The instruments are still relatively expensive, but they're like $80,000 instead of $250,000 for analyzing water isotopes. And it's through a new technology called cavity ring down spectroscopy or off-axis spectroscopy. And so it's easier to analyze many more samples. And so I think that that has opened up much higher resolution monitoring, both spatially and temporally, of oxygen 18 and deuterium in water samples. And then in David's question, the longer water stays in groundwater, the higher the TDS will be. Okay, so David, what's happening is that in the case study in the Wilcox Aquifer, what's happening is that the TDS is not necessarily changing that much, but rather the individual solutes that make up the dissolved solids are changing. So basically, iron decreases, but something else is increasing. Calcium decreases, but sodium's increasing. Sulfate decreases. Sulfide increases, but some of that precipitates out. So ultimately, one of the limits on how much the solute concentration increases is equilibrium. In other words, if you get to a point where you dissolve enough out that you start to precipitate out that a particular compound, then that will limit the concentration of that compound. Now, if you have ultimately a deep groundwater flow system that is coming into contact with minerals like gypsum or halite that have very high solubilities, then they can continue to dissolve. And so ultimately, in some very deep aquifers along very long flow paths, you may have relatively saline groundwater just because the groundwater has been in the subsurface for a long time. And in the process, it has dissolved minerals that have relatively high solubilities. I hope that wasn't too complicated an answer, David. I didn't show examples from other types of flow systems, but there are other studies out there that show regional flow systems with much higher salinities for much older waters along longer flow paths. Okay, so Gananjar. Different locations have different hydrogeologic conditions relative to seawater intrusion. What's the parameter causing the intrusion? Typically, it's a change in hydraulic gradient. So it could be a rise in sea level. It could be a lowering of the hydraulic head in the coastal aquifer due to pumping or due to digging of drainage canals. So really, it's physically driven. In terms of current daily products that have dangerous contaminants to groundwater, oh goodness, there are so many different ones. In North America, we're starting to worry more about a class of compounds called PFAS or PFAS, which are perfluorinated alkyl substances. So if you think about Teflon, like coating on frying pans, for example, those compounds are very widespread and we still don't know their human health impacts. And so we don't quite know how dangerous they are yet. I would say the dangerous products still are things like gasoline. Or if you consider sewage a product, I mean, it is kind of, it's not a manufactured product. the microorganisms in sewage are perhaps the most dangerous contaminants. So that argues for, the importance of sanitation. Okay, so Great Salt Lake. When I talked about estimating evaporation and estimating groundwater recharge, different components of the water balance equation, the Great Salt Lake is what's known as a closed basin. And what that means is that the only way out of the basin for the water is through evaporation. And so what happens is the water flows either through rivers that flow into the Great Salt Lake or through groundwater that discharges at the Great Salt Lake. And the salt is formed by the evaporation of the dissolved salts in the groundwater or the surface water. Not all of the water evaporates in that case, but a lot of it evaporates. And part of it's because it's an arid environment. You have high temperatures and low humidities. The rivers and the groundwater are coming from surrounding mountain basins. And throughout the Western United States, you have those sorts of closed basins like that. And it's not just in the Western United States, it's in other areas as well, like Central Asia. Think of the Caspian Sea, for example, or the Aral Sea or the Dead Sea in the Middle East, or Lake Erie in Australia. Okay, are there any other questions or comments? These have all been excellent questions, and you all have been very patient with me in terms of, I'm sure I talked fast. Even though I tried not to, and because you are engineers and I'm a geologist, I'm sure I use some terms that are not familiar, and because I'm American and you're Indonesian, I'm sure some of the geographic references were not as familiar. But Jadvan has my contact information. Feel free to pass on questions through him. And as he and I were discussing previously, I hope to be able to come to visit Brawijaya sometime next year, either January or perhaps more likely in May, for a couple of weeks to do more kind of hands-on things where we could go out into the field and measure stream flow, and we could do karst investigations in the area around Malong and things like that. And I could also talk about other things that are not specifically scientific, like writing technical papers and applying to graduate school and writing research proposals and things like that. So those are things that I hope to be able to do during a visit.
Yeah, that sounds good, Professor. Maybe we can discuss about that program later.
Yeah, absolutely. And you all are in for a treat tomorrow. Carmen Agaritas is fantastic. Jadvan's met Dr. Agaritas. She's really energetic. I think she's just a great example. And some of the things that she'll talk about, I think, are really relevant to environmental restoration problems that you may be dealing with. But I suspect that some of the things she'll talk about are things that are new to you. So you all are really in for a good presentation there.
Yeah, I think tomorrow will be more interesting too. So if you allow me, Professor Alan, I will sort this question to you. Maybe if the student or participant want to get full answer, if you talk more quicker, so they can read again the answer for their question. Maybe I will sort the question and send it to you later. And I think our time is also in the end of this session, I think, unfortunately. And yeah, maybe we still have another session tomorrow with Professor Carmen, but I think we can keep in touch with you later. And
absolutely.
Yes, I think we still can continue this collaboration and nice opportunity to collaborate it with student also. And yeah, I think this class is very important for us, and we glad to have you this morning in Indonesia, and you have we also give thank you to you to have time with us today, and we will continue this class hopefully in the next year, I think. Thank you.
Inshallah and terima kasih.
Oh, okay, thank you, inshallah.
Professor
Thank you,
Alan,
Professor.
can we take a picture together?
Of course, of course.
Yes.
Let me put my glasses on.
Please,
So-
participant, can you turn on camera for a moment? While we can take your picture together with Professor Alan.
Oh yeah, 1, 2, 3, smile. Okay. And next slide. 1, 2, 3, and cheers.
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 Yes.
Okay, thank you very much.
Thank
Prof.
you very
Thank
much,
you,
Professor
everybody.
Alan.
Terima
Good to
Thank
kasih.
you
see
for the
you, Prof. Alan,
opportunity.
and so we'll see each other again sometimes in the future.
Yeah,
I certainly
sure.
hope so. Thank you, everybody. I really
Thank you.
appreciate it. It was a great
Thank you.
opportunity. Jeff
Thank
and
you
I will
very
be in
much.
touch.
Yes,
Take care.
we can
Bye-bye.
still keep
Terima
in touch,
kasih,
Professor.
Prof.
Thank
Alan.
you.
Bye-bye. Thank you, everyone.
Bye-bye. Bye-bye. Terima kasih Bapak Ibu sekalian atas kehadiran